universal. B stands for beam. Now we use simply UC, which is simply universal column, and WC is the welded column. Right? So that is actually the difference to in the designation to a beam. So you see that actually on the second letter. Right? And again, the same terminology for the designation and also the meaning of the numbering. The number in front of it represents the depth of this the depth of the column, and the number behind is the weight per meter. So there's an example I simply said about, these are examples which comes from the catalog, I think. Some numbers are simply made up, right? But it's exactly the same as for B. With the steel, exactly the same, there's nothing to explain. We use the same terminology for the steel grade, whether 300, 350, 360 or 400. So we see basically the steel grade, which is simply the strength of the steel if we do not know the designation, if we do not know the steel. So here for the column, the supports are much more limited. Right? In fact, we have only the rigid support, as you can see here. That's a photo of myself from my train station, where you see such a column is actually simply concreted into the floor. Right? So if you just go to the next train station, then you see the supports for the roof or for the poles there. Then they usually concreted it like this, which means that's a fully fixed support. A simple support is something like this. It's also for when I just walk by. This one is a good example also for your project. So it's actually bolted. There's a foundation underneath on which they simply bolted it. Right? This one is not a fixed support. This is a kind of hinge support or similar. Right? So these are the basic ones. So you do not see a hinge support, right? So we will not do this, right? And it will not be a roller support either. So in essence, we will actually look at this one, and later on in your project, you will look at this. It's pretty straight. Actually, Space Gas will give us that. Right? So remember, as soon as you have a rigid or a fixed support, at that support, you have bending moments. Talked about that yesterday with the same when we had a beam fixed on both sides. Fixed on both sides means bending moments. And that helped us to identify the different cases in our standards. So far, there's one little information here which is not what you would see in a beam. It says here the simple support, it says at each end, lateral translation is fully prevented, but rotations, and now there's a little information is said about beam main and minor axis. Actually, it's supposed to be column. Just for this one here, let me just change this. Column. So this is a term which basically will be only appear in our steel column. What is a main axis? What is a minor axis? Or minor axis. So now for the column, they are here just listed. I think there are even more than that. There are at least 4 possibilities to fail. The first one is what is called a compressive yielding. Right? As you can imagine, you actually push it down, right? And if you really push it down and it's very sturdy, so it doesn't do this one here. let me show the difference between something like this and this. So if you actually really try to squish it down, it will definitely more likely deflect or buckle, right? Because it's much longer. It's very delicate, right? Slender. So even if I be exactly pressing it, it will never compress because it's simply too delicate. Having such a sturdy one like this one, that's what you see there. On a short one, if you push it down, it is more likely that I can squish it. So that's one kind of failure. The other one is buckling. Is that about buckling in an elastic and inelastic? Elastic is what I simply show when you walk over something like, as I said yesterday, when you be on a patio, on a crane slender, they have this little slender steel and you stand there, and sometimes you can see that it shakes, right? Or on the bridge. So if I squish it like this, then it will do this. Right? As long as it's within the limit, then it actually goes back. So basically, if I just release it, it goes back. The problem is actually, it's not supposed to happen, but because I feel uncomfortable. If you stand on a bridge like this and you feel it wobbly, that's insecure. But per se, it is actually not a failure of the material or the failure of the column, it is simply the failure of the construct. Right? It's not supposed to happen that, for instance, a column buckles really like this or this. And here's then the opposite, that basically if you just go too far, that's the irreversible, that means it's happening like this. Right? So if the load is too high and it buckles too far, then it simply bends through, that yields here, which means that one is irreplaceably and erratically damaged. And local buckling is simply here, that you see there's actually no buckling, but at some location there is. So which means there's only at certain locations, here over the entire column, and here sometimes here locally, only on particular spots. Wherever these spots are, that cannot be predicted. If you just have a load like this and you want to test it, you do not know where the local buckling really occurs. Because it depends on the material history, it depends on the load, it depends on, I do not know. So these are really unpredictable locations, but it occurs. So all of them, as you can see here, there's another example. That's where we have a load up here, an axial load. Right. It applies to this one, and then actually causes all these different, what we see here, failures. So we have to consider those and incorporate it into our dimension. And of course, depending on our cross-section and basically our design of our cross-section here, whether a beam is more likely, a column is more likely to squash or to buckle. If you have a short one, it's very unlikely that it buckles, right? It will never buckle. It will only, the maximum will happen with this one. If you have a slender means slim, long, elongated, like this one, it's almost impossible that it would squash. It will definitely fall before failure because of the buckle. So simply common sense. I mean, when you see that, that's really delicate, right? So how do we consider that? Or how does the standard consider that? Pretty much the same way as we talked about yesterday and the stream before. We check the capacities. The capacity of a column. So as I can say here, that's what I already say here, written down. There's only that word slender or slenderness, right? When you hear slenderness, that simply means it is a very long, elongated structure, and also it's called the slenderness ratio. That's the number which describes basically the ratio of the length versus the cross-section. In whatever way, we will calculate this number, right? It indicates a long column, very highly susceptible to buckling. If it's a small one, it is more less broad. So that means one idea, when we have a chance to basically control that ratio, is to make the ratio as small as possible if you do not want to have buckling, for instance. But the point is actually really here that number here when we talk about slenderness. Simply the ratio of this length and the cross section. Surprisingly, we have to consider only two capacities. Yesterday we did with the beam, we had the section moment capacity and the member moment capacity, the whole beam, right? Here is exactly the same. We consider the nominal section, but this time it's not a moment, a bending moment, it is now a compression force. Right? That's why I said about compressive capacity. That means that is now force. So the beam bending column is a force. And also the nominal member compressive capacity, that means basically over the whole. Pretty much the same as we had yesterday. And of course, we have also those two scenarios. Either the steel beam is given, the steel column is given, then we have to check or verify the loads, the maximum loads, or check whether the loads we have are good or not. And the other option is we have to find that one. And that's the one which we definitely have to go for, because that's actually our task, our dimensioning task. So we want to find a column when there's a certain load, the known load or situation is given. So again, write down section capacity NS, that is actually my section compressive force, and the member compressive force. Capacity. The member capacity is what my steel column is able to withstand. And that's checked against the design load. So that sets the stage. It's exactly the same thing. And how to calculate it is almost the same. Only the process is a little bit different, but we do again check this one. The section again is described now. The nominal section, that means the compressive force, is described by what is called AE, which is the effective cross-section area. You have to check the slide next one. And Fy, which is again our steel. Nominal yield stress of steel. If we do not know the steel, the column yet, then we use the general grade, steel grade. If we know it, then we use the one from the table. As usual. Remember the steps again. If you do not know our beam, if you do not know our column, we use the steel grade, the number, as our initial nominal yield stress. And once we found it, then we recalculate it, but this time with the number which is inside the table. Capacity reduction factor, we talked about that, that's already here. I just put it up here this time. It is 0.9, which means it's the same as for the beam. But otherwise, exactly the same, right? That's my design load, and that must be smaller or equal than my section compressive capacity times that reduction factor. Let's look at the effective cross-section area. What does this mean? So it's actually calculated in a particular way, which also comes from the standards. It says about that effective area is simply a form factor, which simply is some sort of a geometric factor, which is also in the table. We find that in our on-steel catalog. And AN is simply the net area of our steel column. Right? And that actually has been introduced, for instance, if you have in the column a cut or a hole, something like that, in the cross section. Right? But that means that's the area of the total cross section minus holes or cutouts. So if you have no holes, no cutouts, or no penetration or whatever, it is simply our nominal steel cross section. Right? And of course, this will always be the case. We will always use our nominal steel column cross section, which comes also from the table. That has to be simply multiplied by TF. So we do not assume any holes or any cutouts. But in order, if you want to find out, if you want to find more, that is actually the approach. So you have to find AN, which comes from, well, I just didn't want to actually add extra slide for this one, and multiply that by KF. So this one, and this one is in the catalog. So that's the effective area. Here is now how you actually calculate the whole thing. Looks awful, and actually it's awful. And of course I do not bother you with this because this is actually how you actually determine now the effective area, having, for instance, such a complex structure like this. Right? We actually will calculate it in a different way. Right? So we do not actually look at this. I just have it only there because it was originally in the slides. For whatever reason and for whatever purpose it was, we will not cover it. We simply assume this, and this one I simply brush over and just leave it. Because we want to be practical, we want to be working with tables with basically as much help we can get without having strained our brain with this one. I'm going to take it out probably for the next version because I think it doesn't need to have anything. Here is actually what matters. That's for the welded beam and for the welded universal columns. There you see in that table number 10 and number 16 respectively, you see that form factor. Right? Here's the form factor, here's the form factor, and so on. So here you simply click and choose. So far, nothing dramatic here. So let's have a look. There's an example. I said about determine the nominal section capacity of a concentrically loaded 250 72.9 column of grade 300 plus, if the effective length is 4 meters. Right? That's a simple example. You have to calculate NS. Here, NS is given by that equation which you just saw. The steel designation is known here. Check the catalog. Check the catalog. Here's my beam column 250 72.9. There's again two different yield stresses, one for the flange and one for the web. Right? And we always choose the lower one because for safety reasons. Right? We always use with the lower number. Okay. FY. So AE, we have to find that too, and if I have done this correctly, then I should see that here too, which is simply my cross-section area, AE. Because remember, we say we do not have any holes or any penetrations or whatever you want to modify such a cross-section. We simply assume it is a pure, simple column with a cross-section like an eye cross-section mostly. And that means that we simply use 4AN. That means our effective the cross section. And AG is then 9,220. And then finally, right, you multiply together. Right. So here for this particular one, AE equals KF times AN, which is the same as KF times AG. That was 9,320, this one. And KF is 1. KF is 51. Actually, that's wrong. Sorry, that's not millimeter. It shouldn't be millimeter because KF is a factor. Factors usually don't have dimensions. So that was my mistake here. That should be millimeter. Delete. Okay. F. So that means we have this, we have this, that means we have this, then we have this, and now we can simply calculate NS. And if you just do that, then make sure that you have millimeters. I mean, everything is millimeter. So that means we get a compressive force capacity for this particular cross section of 2,796 kilonewtons. Make sense? Or any problems? Tell me. Or good? Or is there I probably can imagine that it's probably confusing with the different areas, right? But in the essence, you have only one area, which is my cross-section area, multiplied by the form factor. That gives me my effective area, A. That's it. That's NS, or the section capacity, the section compressive capacity of that. Now the next thing, as you can imagine, the same thing with the beam yesterday. The cross section was very simple to calculate, but for the whole member it was more difficult. There's all these equations yesterday. This one here is also a bit more complicated, not because of the equation it looks like, it is simply how it's set up. So here, the equation, first of all, that nominal compressive section, the member one, is basically for the entire column. Right? And that is actually calculated by what is a number which is called alpha C. That's what they call a slenderness reduction factor. And that one is calculated by this equation. Right. It is given with a letter, actually let me say that because that's when you want to find the Greek letter. That's the letter Xi. This one is lambda. And this is the equation for alpha C. Which means you need to find my compressing member factor and the slenderness ratio. And we have to find those two first, next, in order to find this. How do you do that? That's how you calculate it. So you have that C is given by my lambda, which is still my ratio, and there's another letter here. That's the third one now. It's called nu, or eta. No, sorry, that's eta. Not nu, that's eta. And that is calculated again by this expression, which contains the ratio. Right? And this ratio now is again calculated by another number multiplied by two other factors. So you can see it is stacked. You start with this one, then go to the next staircase, going up the stairway to heaven, which is then alpha C. Right. So you see, so number 2 is alpha A, which is calculated by this. So we're definitely going to use XL for that, simply for the calculations. And that member section factor, which you have to find in the table. I hope that PowerPoint makes it clear how to actually get all these things together. Because otherwise it's simply showing you and applying it. That factor is depend on the form factor. Form factor is given for that one. Now we have to check at the different properties of my element I have. So for instance, it said about it is a hot formed right hand side, or I do not know what that actually stands for. I have no idea what that is, to tell you the truth. Go next one, the cold form RHS and CSH. I'll just check it out. I have to let me write down. I want to find what that is. I never really bothered with it because the only part which is really interesting, and that's actually the one here, down here, hot rolled UB and WC, welded H and I sections. Right. So which one? U, C, and UB. Welded H and I sections. Here is basically up welded H and I section fabricated from S-rolled plates and so on. And here, for instance, the hot railed UB and UC for flange thickness 40 millimeter and more. Super big, right? So which one to choose? Here's another one, right? It says here now, hot rolled UB and U sections, welded box sections. So that means if you have a UC, that means you have universal beam, universal column, then you'll see that factor alpha B is 0. Here, the same. So that means any universal column or any universal beam, that factor there is 0. Otherwise, you have to find it from your different combinations. And in fact, it's only we have only universal columns and universal columns. So that is probably a bit difficult to interpret. CHS. Just want to know what that actually is. To tell you the truth, I never really cared about looking into all the details. The only thing what I cared about is this one here, because we have only universal columns and beams at this stage, which means it will be 0. In other words, for this particular case, alpha B is 0. Okay. And then finally, we have to find this one, alpha N. That's the most complex thing, which I need basically to explain a little bit more. So, when you look at this alpha N, which is here, right? So alpha, that's actually our slenderness factor or slenderness ratio of our column. It's calculated by alpha N, lambda N, which is this one here, sorry, this one. Alpha A we saw in the previous slide, and alpha B we saw also in the previous slide. So it's actually now hanging on this one. And this one is the most complex stuff, because now we have to look at the equation. The equation is a bit different because first of all it contains what we call the effective length. LE is the effective length or the affecting buckling length. But we'll see what that means. Then R is the radius of gyration. This one is not probably familiar to you, but you had some relations to it in stage 4. When we talk about inertia. Let's have a look at this. I'll try to show it here in that example. Remember inertia. Inertia is simply the resistance of a beam or of a column to be deformed or changed. It's simply the resistance. It doesn't want to be shaped, it doesn't want to be bent, it doesn't want to be whatever it does. And that depends on inertia. So for instance, when you look at this one and you calculate the inertia, that means, as you can see, if I use the same load, it will bend much less than this one, right? So if you have a plank over the bridge, right? Because the inertia of this is different to that. Right? I'm not sure Matthew showed you the example. That's a prime example when you look at, when you go, for instance, roof design. When you go to the roof and you go to any construction site, then you see those roofs, those constructions, they're always upright like this. They're never put like this. It is simply here, just because that one bends much better than this. So the question was here, how to calculate the inertia. And what is actually the inertia? I'm not sure, again, Matthew probably can tell. So let's simply say we have an inertia here of the I-beam. Okay? Say, here's our x. Remember yesterday you used, for instance, Iy. Right? You probably saw yesterday Iy, and that was the inertia about the y-axis. So what is inertia? It's nothing else. Simply imagine this one actually is split up into little squares. Millions of them, thousands of them, right? This one has a certain area, which they assume is always the same. And now the inertia says that you basically determine from here the distance to here, to my x. Right? This is a distance. It's called a radius. And now you do this for all and add them up. Sum them up. And that, the total number you get, that is the inertia. It's an area mark. So now you can imagine that the radius from here to here for this element is completely different than to here. Which means the inertia for y direction is a completely different than Ex. So this one here, for this one, Iy, Ix is definitely not the same as Ay. In fact, this one here, Ay, this one is much smaller than Ax. And that's actually simply so on this point, and again, this is the distance from here to the point, to the center point, that's called the radius of gyration. That radius here. It's simply a distance measured from the x-axis, right? And Rx, the radius for Rx, measured from the x-axis or measured from the y-axis. And these numbers are given in tables, of course, because you don't have to calculate. Because it's a complex process, you have to integrate, and that's what you don't do. So with other words, the inertia for the I-beam, we call that Ix. It's related to radius of gyration Rx. And for Iy, X likewise. So with other words, the radius here, there's one radius for X and another one for Y. With other words, there are two equations. Okay. And moreover, you will also see that LEX, LE, that means that effective buckling length, there are also one for X and another one for Y. But that's the most difficult thing to understand, because it's the same, this one is the same I-beam, the same I-column. Why do you have different radius of gyration? It's simply related to the inertia. With other words, this equation will appear twice. One for X and one for Y. So in other words, because that's what I said, there are two values of R for X and Y, and this is actually given. These are in the table, unless it is actually stated specifically that is this and this is this. We will see that sometimes we will see A is my area, of course, which we know is AG, and the inertia IX, which we also know. So that means that actually comes from that's a purely geometric figure, and that's usually given. When you go into the Yvonski catalog, then you'll see RX and R. But we'll come to this one, right? So they are in the standards. And as you can see here, that's where you find them, RX and RY. So this here in particular contains all the information which you need for your column, right? About X and about Y. So here again, you simply have to find the right column and then simply pick the numbers and perform the calculation. Which means now in the end, that's what we need to find out, is my effective length, which is now determined by this. The effective length is a bit more easy, because in the end, it depends only how that column is supported. Right. So for instance, let's say a simple column which goes upright like this. It is fixed on the floor, but like this, and the rest on top is simply do this, right? Nothing. It's like the concrete beam we had. Remember when we did space gas? We had a fixed support down here and left it free up here. So that is the situation for a single column simply hanging in the air, and that's what you see here. They call it a sway member, which because the top can sway forwards and backs. And for this particular one here, the effective that length factor would be 2.2. So again, you see that in your context, in the instruction. Later on, when we talk about our whole structure, then it will not sway anymore. Then we have to choose another factor, but I will explain that a little bit later, right, when we go to the project. But if you just have something like this, column only as a fixed support and free up there, then it is definitely this one. Otherwise, for instance, if you have a concrete a column which is concreted on both sides or fully fixed on both sides, then it's 0.7. Here, fully fixed on that side, and here is a hinge support, it's 0.85. Right? And here are two hinge supports, then it would be 1, and so on. Right? So that factor depends on how you support it. The length is given, and that gives me the effective length. Which means I have now this, I have this, I have this, this, and this, which means now I can find this. So I get one number for X, because that depends on X, and another one for Y. And which one do you choose? Here actually I have another example. I just forgot that I actually updated the whole thing a little bit. So here, for instance, the effective length on this one, blah, 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 blah. The effective length also, if it's not given, right? Sometimes it is actually given that the lengths are determined, LE, which is simply called LEX and LE1. So with other words, for some, it is actually stated. I think the example I'm going to show you, we state the effective length, which means you don't have to calculate it anymore. Right? Here's an example, for instance, one that's a fixed base, and up here it's a pinned one, and it's free in that way. Right? So which means it is actually, what would that be for? Let's say about a steel column fixed to the ground, which is all of those, that means this or that, this one, and restricted on top by a cable in X direction. That's the cable, but here this one, but it can sway in that direction. So which means it is something like this one, I would think. Or this one. It's a pin support actually. Right? That means it would be this. But remember, they are two. Right? In that direction, it is completely free. That would be this situation. And in the other way, it's fixed. It would be this. So here now you really have to think in terms of direction. Supports. In the past we didn't care. We said about fully fixed or not. But for the column now we have to make a difference between either it is supported in that way or that, or that or that. That's a fundamental difference because of the different geometries in X and in Y. We'll see next application and probably it becomes a bit more clear. So again, this one depends also on X and on Y. And then you write it down like this. So for instance, now you get one value for X, call it lambda nx, and the other one for Y. And then you choose the bigger one of those. And that's your lambda. Again, this is in the instruction, that's usually in the table. This one that's actually either stated, you have to calculate it. This one is given in this table. This one needs to be stated or calculated. And the other factors are already in there. So only think in terms of X and Y. I would think let's have a break. It's 10ish, even though we start a little bit late. Then we'll continue with the next one. We calculate NC now for this beam, a column which I simply showed you.